Okay, so you should be able to see my screen now. So thanks for the invitation. I'm very happy to be here. I would be happy to take questions during the talk or after the talk. So I would like to set the stage for the discussion today to talk about robust LSM trees, and I'll present a prelude to robust LSM trees that Andy will follow up after me, essentially, by setting the stage about some of the basic concepts of LSMs and some of the optimization and design decisions that we need to make in order to have good performance. And then Andy will go about the tuning decisions that we need to make. So, of course, we all know LSM. They are used by they are used and developed by a number of companies, right? And the reason for that is because they offer fast writes, they offer competitive reads, and they have good space utilization. And if we see the recent research on the topic, we'll see that there is a very upward trend on interest in LSM trees the last few years, specifically the last 10 years or so, exactly for these three reasons. And of course, for the majority of this time, the question was about LSM trees was essentially about building the system standalone systems. But the last few years, we've actually been considering what happens, what changes when we build systems in the cloud. And apart from LSM, let me just very quickly, on the high level, talk about what the cloud brings. So on the one front, it brings unpredictability. Yeah, we don't have full control or very accurate expectation of the workloads or the access patterns or the ingestion rates of our data. And it also brings unpredictability with respect to compute, memory, and storage. For example, in several cases, we might not be absolutely certain what exactly type of resource will be available to us. And with all these massive deployments in the cloud, small becomes big. So small data, small overheads, small benefits, or even small penalties, small costs become big because essentially they add up by having multiple instances, right? And of course, this when we say costs, it might be energy, monetary costs, but essentially, we typically think everything as monetary costs that encapsulates the whole thing. So in a nutshell, what we are interested more in, and what I'll be talking about today and also Andy later, is about the unpredictability that data systems face in the cloud, and specifically unpredictability in the resources, in the workload that we face. And also, if we have the time, I'll spend a few minutes on regulatory assumptions, specifically about data retention. This is just a small type of problem that is becoming more and more important as we go. So overall, unpredictability hurts tuning and design decisions. And the reason it hurts is because when we try to tune a data system, we need to take into account the details of the underlying hardware, the access patterns and the expected workload, as well as the data size and distribution, in order to find the values and the tuning parameters for the physics of our system, along with the physical design decisions. And this essentially is an optimization problem, while uncertainty sometimes may lead us away from the optimal. In some cases, this is an engineering problem, right? Because we don't necessarily not necessarily able to solve an optimization problem per se. And in this case, still uncertainty may still cause designs to be suboptimal. So if we go back to our LSM-tree discussion, there are two main things that can be affected by the uncertainty, essentially the tuning of the LSM trees and the compaction, which is the core, the heart of whatever an LSM tree is doing to maintain its state and its performance benefits. So I will start by discussing about the compaction, and then Andy will actually discuss about tuning later on in his presentation. So I will continue with the following schedule in mind. There is a very short primer, because I'm assuming that everybody is familiar with LSM concepts. Of course, if there are questions, I guess anybody in the panel are happy to answer about questions about LSM. And then I'll talk a little bit about the design space work. That is the main thing that I'm going to be talking about. And then if we have the time, I'll spend some minutes on delivery requirements and storage variability. And then I will just set the stage with one slide so Andy can continue with the workload uncertainty discussion. So let me quickly start with a primer. An LSM-tree essentially has an in-memory component that collects key value stores, and then it has these components that have exponentially larger sizes with a size ratio T. And the reason that we generate these components is by the so-called compaction process that actually merges files when they have a big enough size. And while compaction typically happens between entire levels, many systems have adopted the partial compaction strategy, where we compact only when the size of a specific level goes beyond the threshold by pushing the data from memory, and then we select one of the components in this level. Note that in this notation here, every level contains separate components, physical separate files. However, the entire level is overall sorted. So we take only one small component, in this case, the star one, and we merge with the overlapping components of the next level, so we don't actually perform a full merge of the entire levels, which sometimes leads to unnecessary data movement. And of course, we're going to keep doing that. So once with some level is out of the threshold, we will pick one file and we will merge only with the overlapping files, in that way amortizing the compaction cost. Okay, and just to have a quick discussion about how LSM-trees actually answer read queries. The way it works is that we have a variation of fence pointers or zone maps, that essentially this is very small metadata in memory that allow us to perform whatever binary search we have to do for every sorted level, to perform it in memory, and then we go to the disk. And to also avoid the unnecessary accesses whenever the value we're looking for does not exist at all in a specific level, typically every LSM is also equipped with Bloom filters, which are queried first, and then we can actually completely skip going to the data for that specific level. To see this query in a little bit more detail here, we're looking for a key 5, for the key value with key 5. We go to the buffer, we don't find anything in the buffer, and then we have to start asking the different levels of the tree one by one, starting from the top one because this is the most recent data, going to the bottom one. And we first ask the Bloom filter if the Bloom filter let me see. Okay, if the Bloom filter, I just want to have a pointer, right? If the Bloom filter says no, then essentially we're going to skip entirely this level. If the Bloom filter says yes, we're going to find the page that will contain the value that may contain value 5 that we're looking for. This might be a false positive. In this case, it is. So we have to keep continuing, and we're going to go to the third level. The Bloom filter would say yes. The fence pointer will take us to the corresponding file and page, and we'll find the key that we're looking for. Overall, every read query will have to go up to the whole L levels, where L is calculated as the logarithm of the total data size with base T, where T is the size ratio of the tree. So this is some, common principles about how LSM-tree works. And what I want to highlight is that LSM is actually very powerful. Like even the basic LSM is very powerful because essentially it can navigate performance trade-offs. On the one hand, we have a memory versus read performance trade-off. We can actually allocate more memory to our Bloom filters, and we can have fewer false positives. And on the other hand, we have a reading versus writing trade-off. We can perform more merging, more aggressive merging by changing the tuning, the size ratio that is, and the merging policy, tiering versus leveling, for example. And if we perform more merging, we're having fewer runs, but by doing more merging, our writes are actually more expensive. So here we have a read cost versus update cost trade-off. By more merging, we have fewer runs to search. So more writes for more expensive insertions for less expensive read queries. So this is a very quick primer of the trees. I would like to continue my discussion and maybe pause later on for questions. And of course, after for the Q&A, so we go into the meat of what I would like to present today. So the next part of the talk is about the LSM compaction design space. So I did mention compactions here, but I would really like to dive deeper into what the compaction is. So first of all, the compaction affects a number of metrics or behaviors, let's say, of the LSM-tree. It affects space amplification, write performance, scan performance, lookup performance, delete performance. All of them are affected by the compaction, and we like to understand what are the options, how they are affected, what can we do, how should we design, how should we pick, let's say, our compaction policies. So what we'd like to do here is to be able to understand if I have a workload and a tuning, what would be the performance, either qualitatively or even quantitatively. Our goal is to be able to pick and design compactions and answer complex design questions. And we do this by breaking the black box about what compaction is, and by actually learning from a lot of experiments, collecting lots of data that we summarize today in just a few graphs and a few takeaway messages. So let's go back to the basics. The compaction is a process that happens between two levels when the levels have grown out of size and we need to merge them, so we make more space at the upper level for new data to come in. This is the full compaction when we merge the full levels. We also have the partial compaction when we merge only a small part of the levels. We'll see that in more detail. So in order to classify and understand what are all the possible choices, we sit down and thought about 4 fundamental questions. The questions go as follows: how to organize data on the device, how much data to move at a time, which block, which part of data should be moved, and when to reorganize the data layout. And essentially, these questions are actually, we codified them as 4 dimensions, named data layout, compaction granularity, data movement policy, and trigger. Remember, the LSM-tree, what it does is that when a key value entry is inserted, it goes to the memory buffer. When the buffer is full, we have to flush it on the disk. Now, if there's nothing on the disk, that's fine. If something is on the disk, at some point, we need to merge files. We need to reorganize the data on the disk. How do we do this? When? How much data? All of those questions are exactly the questions that we're answering now in the compaction design space. So let's take them one by one. Data layout. The data layout that we see in LSM-trees today is essentially the number of runs per level. The most classical example is tiering and leveling, right? So tiering and leveling means that even though we have this hierarchy of data collections that have exponentially increasing size, in the leveling side, on the left-hand side, we're performing eager merging, meaning that every time we accumulate data in the same level, we are merging them, so we have only one sorted run per level. While on the tiering side, every time we are storing something on the disk, we just put a single file there and we do nothing up until we accumulate a number of files, and only then we merge and push to the next level. So essentially, we are performing more merging on the left-hand side, hence the eager in parentheses, and less merging in the right-hand side in tiering, hence the lazy in parentheses. Clearly, if we are performing more merging, then this is better for reads, the leveling case, and less merging is better for writes. Of course, there are in-betweens as well. And essentially, many systems opt to use one leveling or L leveling in their internal design. Maybe they call it something else, but essentially, it uses one level that has tiering. This is the one leveling, or all levels have tiering except the last one, the big one at the bottom that has leveling, because it will be very expensive to actually go and search the whole last level for the data. So there is the whole spectrum between leveling, tiering, and the hybrids in between. The second question is the compaction granularity, or data moved per compaction. And the options for that is that we can actually move entire levels, or we can move files per level, or we can move sorted runs within a level. So this is the granularity that we might get in any compaction. Now, once we have the granularity, once we allow files to be moved, the question is which files to move. As we saw before in the primer, we might pick one file to push to the next level. How do we pick this file? And there's actually a number of options. So we can pick files with a minimum overlap with the parent level. We can pick the coldest file, the file with the most tombstones, where tombstones invalidate other data, or we can pick a round-robin file in a round-robin fashion. So the fourth question is the compaction trigger, when to invoke the compaction routine. And the options here, again, there are several, but the main options are the level saturation, so whether the level has grown to fulfill a specific size, right? There is the number of sorted runs, whether essentially we have accumulated a number of sorted runs and we need to actually reduce the cost of searching because we have too many of them. The age of a file, how old is a file, because this might mean that this data is not relevant anymore, so let's push it, maybe it will be reorganized and even invalidated partially. And space amplification, right? So maybe we have a lot of data, a lot of duplicates, let's start merging so we have fewer duplicates moving forward. So these 4 questions, these 4 decisions about data layout, compaction, granularity, data movement policy, and compaction trigger are essentially able to synthesize, to the best of our understanding, any compaction algorithm to date. And in fact, in our paper, VLDB paper from last year, we have this detailed table that we show for several systems and or papers and academic approaches, what exactly this combination of decisions have been used for their compaction strategies. I'm not going to go into all the details here, but I welcome you to go to the VLDB 2021 paper to see this table in more detail. So let me now talk a little bit about our experiments and show some of the highlights of the results. So we actually implemented in a single system to have an apples to apples comparison in RocksDB, the basic all the options, and we synthesized 10 state-of-the-art compaction strategies, and then we experimented with different workload compositions and data distributions, and we also varied the LSM tuning to see if there is any correlation between tuning and compactions. So overall, we collected 612 different metrics for each one of the 2,000 experiments we executed. And now I'm going to present a very short summary of all these results. First of all, what are the 10 policies that we implemented? The first one is full compaction, which is essentially classical LSM merging of an entire level. So every time we have a level and it's full, we have to merge it entirely with the other level. And if the other level is full, this will trigger another compaction, and so on and so forth. Here on the table, I'm actually listing the options, the decisions of each one of the options that we were discussing before. So what is the layout? What is the granularity, data movement, and compaction trigger? So for the full, the layout is leveling, compaction granularity is levels, entire levels. There's no data movement because we push the entire level, and the compaction trigger is a level saturation. Now, the next two policies, codified the low plus one or a low plus two, are essentially partial compactions that select for pushing to the next level the file with the smallest overlap with the next level, or with the smallest overlap with two levels down. This is LOP, least overlapping parent, and least overlapping grandparent. And these are essentially strategies that aim to reduce write amplification. The next group of 3 strategies, called all the round robin, are again partial compaction strategies that the data movement policy is the oldest, the coldest, the oldest, and the round robin decision. And again, the trigger for all of them is level saturation, meaning that whenever the level is full, we have to pick one file using either the coldest, the oldest, or the round robin. All of them aim to help read queries in different ways. Then the other group is delete oriented policies, but essentially the main difference is in the data movement. Instead of picking files based on whether they're cold or old, they select the files with the highest number of tombstones, or on this case, or the files with expired tombstones when tombstones have a time to live. So meaning that a delete has to be pushed immediately down to the data. And so this is data movement policy, and the trigger, so the moment that we actually perform deletion, is either when we expand the threshold beyond a tombstone density, so when we have more tombstones than a specific number, or when we have tombstones that are older than a specific threshold that we cannot, that we should not allow in the system. And then the one before the last policy is tiering, classical tiering, meaning that essentially we never merge sorted runs within the same level, except when the level is completely full and we push things to the next level. There's no data movement policy over there, but essentially there is a compaction trigger, which is the number of sorted runs. And the hybrid, so of course tiering aims very insert heavy workloads. And last but not least, there's a hybrid approach, one leveling, that has tiering on the first level and leveling on all the other levels. The granularity is the whole sorted runs on the top and only files on all of the bottom levels. And there is no data movement for the first level because we just wait for many sorted runs to be inserted, while there is a least overlapping parent data movement for the remaining levels. And the saturation is number of sorted runs or the compaction trigger is number of sorted runs or level saturation in the other case, in the remaining levels. So, and this is essentially a hybrid that aims to absorb inserts, but also optimize for reads. So it kind of tries to be the best of both worlds. Okay, so now that I have described essentially 10 of the most widely used compaction strategies in LSM systems today, let us see how they compare between themselves when everything is on the same system and the only difference is the compaction and not the implementation of the system. So the first graph here shows the total data movement during a mixed workload of reads and writes. And here we see only what happens as part of the compaction, right? We don't care about anything else. And we see that the green line shows what is the actual data size that was ingested in the data. And these bars show the total data movement that had to happen because of the compactions. So there's no surprise that full leveling does a lot of reads, rereads, and rewrites because it has to push everything in every level as we insert data. All the data have to go through all of the levels. On the other hand, tiering performs much less reading in order to rewrite, essentially, right? And this difference is 5x or more. But most notably, what I would like to point out is that by moving from full leveling to partial leveling, by moving from full leveling here to partial leveling here, we already see 45% less data movement just because we don't always push entire level. So even though some systems use full leveling, partial leveling comes with this immediate benefit for less data movement. And of course, one leveling, which is it's partial, but also has some sort of tiering on the top levels, is actually on the lower end or the best end of that comparison. Right, tiering is about 75% less than leveling, which is expected because we perform much less rereading and rewriting at the expense of more expensive read queries, of course. Right now, so this is now this is the tail write latency. So we want to see what is the worst case performance of our system. So if we want to give an SLA to the user, what we would say apart from the data movement, and what we see here is that again the hybrid policies win, and in fact the LO+1, the least overlapping parent, is by far, along with the cold, the two policies that perform the best. And tiering can have way expensive, way high tail write latency. The reason being that at some points we have to actually merge multiple files in one go, and this means that a single insert has to wait for a merging of tens of files to be serviced. So this tail latency actually becomes pretty bad. All right, now when we focus our attention to the read performance, the difference is not so big, but there are still some interesting observations to be made. So here we vary the percentage of empty point lookups from 0 to 1. So on the left-hand side, 0 means that all of the queries actually are looking for something that exists in the data set. And when alpha is equal to 1, the empty lookups are 100%, meaning that no query finds anything in the data set. And what we observe is that one leveling dominates the whole spectrum, the green line here. Tiering is essentially very bad, especially for empty queries, because it has to read a lot of different files just to find nothing, right? But we also observe that there's a U-shape, right? So let me talk about these two observations. So why one leveling is better? So one leveling is better because when we're performing partial compaction in full leveling, every time something is full in the first level, it will trigger multiple compactions of a single file across every level. So every time we have a compaction, many files from the top part of the tree, which has the most hot data, will be invalidated because as part of the compaction that is happening. However, one leveling allows for multiple files to be accumulated in the first level, having this hybrid tiering approach. Hence, doesn't invalidate so aggressively the cache. So there's bigger benefit, let's say, of the available caching that we have through the hybrid one leveling approach. Something which is not necessarily clearly intended by the compaction design. Rather, it is let's say, a nice byproduct of that design. Now, what about the U-shape? The U-shape is also very interesting. Essentially, what this means is that if I have only empty queries, sorry, this is over here, or if I have only non-empty queries, my performance is better than the mix. And the reason is that if I only have empty queries, then essentially I really need to use my Bloom filter more. And if I only have non-empty queries, I really need to use my indexes more. While in the middle case, I have to use both of them, and I'm getting misses, and I have to fetch data, fetch blocks for both index pages and filter pages. All right, so to wrap up the discussion about read performance, we also saw what happens when we change the distribution from uniform to Zipfian. As we can imagine with Zipfian, things, and this is actually an observation that probably can be seen across other places, but there's the benefit of caching is higher, right? So we observe that essentially, specifically for empty queries, the benefit of caching is so high that there's no difference between all of the approaches. And overall, the difference between the approaches is smaller, exactly because there's more data that are being cached in memory. Okay, the last set of experiments to show for this analysis of compaction is what happens when we change the update to insert ratio. And what do I mean by that? Here, the x-axis shows how many unique inserts we have, essentially, or how many repetitive inserts that invalidate previous values of a key. So if this value is 0, this means that everything is a unique insert. If this value is 8, this means that for every unique insert, I'm going to insert another 8 updates of the same key that invalidate the previous values of the key. And what we observe here is that the right amplification for all the approaches increase with the update to insert ratio, because essentially we have a lot of invalid data and a lot of repetition in our key value SST files throughout the LSM-tree, while for the tiering case only, because we very lazily perform merging, and when we merge, we can get rid of many invalid entries. We have very small increase. You can only see marginally here increase in rate amplification, right? Now, the flip side of that is the tail compaction latency, and different to before. What we observe here is that as we have more and more updates to our data, even tiering actually has much better tail compaction latency. And the reason is that when we compact with tiering, we can actually get rid of a lot of data. In this case, if you think about it, in this case over here, we are getting rid 8 out of 9 of the data, so 90% of the data. So every time we merge, we can get rid 90% of the data, because we have all these duplicates, which we cannot do so aggressively, so eagerly, let's say, with all the other policies, because we are merging more frequently, so we don't have the opportunity to reduce the data size by removing the invalid entries, because we don't have all of them together. So this completes some of the highlights of this analysis that I would like to share. And I would just very briefly point out that the relative benefits and the relative behavior of different compaction policies did not change as we change the tuning. So the discussion about tuning that we're going to have is essentially an orthogonal discussion to the one that we did up until now, which is what compaction strategy I want to decide if I want to optimize for a specific metric. Now, once we make this decision, then we can actually make a different tuning decision to make sure that we can get the best value for the specific metric, right? But these are two orthogonal things that can be combined, and essentially Andy will be talking about that. So I don't know if I suppose and see if there's any questions, or should I continue to finish essentially the presentation? What should I do?